For clarity, let's add the shapes of our different matrices and vectors as comments. So our input matrix X is of shape 404 by 13, 404 by 13. So we have our target vector Y, which is actually a list of 404 elements. Moving down to the output of the hidden layer Z, because we have two neurons in the hidden layer, Z is a 404 by 2 matrix, and our prediction vector ypred is a 404 by 1 vector. Now, let's get to our backward pass. We saw that the partial of the loss with respect to y hat was equal to the difference between our prediction vector and the target vector. Let's call that partial grad ypred. So we saw that grad ypred was equal to the difference between our prediction vector and our target vector. So what I'm doing right here is I am making sure the shape of our target vector actually match the shape of our prediction vector. So I'm using the numpy reshape function, to which I will provide our target vector, and I will also provide the desired shape. There we have it. We have the partial of the loss with respect to y hat. And let's actually add its shape so that we are consistent. So we have grad ypred, which should be of shape 404 by 1, because it's the difference between two vectors of shape 404 by 1. Moving on to the partial of the loss function with respect to the wave vector of the output layer V, we saw that that partial is equal to the dot product between the partial of the loss with respect to y hat that we just computed and the output of the hidden layer Z. Let's call it grad V. So grade V will be equal to grade ypred dot Z, and grade V will have a shape of 1 by 2. This partial is a 1 by 2 vector, but V is actually a 2 by 1 vector. So if we are to use this partial to update V, we will need to transpose it. To avoid doing that later on, we can just change the order of the elements in the dot product and obtain a 2 by 1 vector. Let's go ahead and do it. So we will go with Z, and we will take a transpose so that the dot product is doable. So we will go with Z dot grade ypred, and the result would be a 2 by 1 vector. And there we have it. We just computed the partial of the loss function with respect to the wave vector of our output layer. Next, we are going to compute the partial of the loss with respect to the weights of the input layer. We have applied the chain rule and we have calculated the partial of the loss function with respect to the weights of one of the neurons of the input layer. We obtained the dot product of these three elements, where Wj are the weights of the neuron of interest and Zj is the output of the neuron of interest. The neuron of interest being the neuron of the input layer we are looking at. Because the dot product is associative, We can start by computing the dot product of the first two elements. According to the chain rule, this is actually the partial of the loss with respect to Zj. Zj being the output of the neuron of interest in the input layer. Let's go back to our code to compute it. We just saw that the partial of the loss with respect to z is equal to the dot product between the partial of the loss with respect to y hat and the partial of y hat with respect to z. Let's call that partial grade z. So we just saw that grade z is equal to grade y pred dot v, because the partial of the loss with respect to y hat is grade y pred and the partial of y hat with respect to z is the wave vector of the output layer. Let's go ahead and add the shape of this gradient. So grade z dot shape is equal to 404 by 2. Notice how I extended this partial derivative to the two neurons of the input layer by providing wave vector v instead of wave vector vj only. This worked fine because by providing wave vector v, we will obtain a 404 by 2 matrix where each column will hold the partial of the loss with respect to output zj of one of the input layer's neurons. Now, to obtain the partial of the loss with respect to the weights of one neuron in the input layer, we need to compute the dot product of the partial of the loss with respect to zj that we just obtained and the partial of zj with respect to the weights of the concerned neuron. We have the partial of zj with respect to wj equals this modified version of the input matrix where every sample that results in a negative dot product with wj is essentially nullified, and this happens because of the ReLU function. Now, each sample has 13 features. So if a sample is replaced by the null vector, we essentially replace each of the 13 elements of that sample by 0. As a result, when computing the dot product of the partial of the loss with respect to zj and the partial of zj with respect to wj, the cancelled samples will essentially nullify the elements they are multiplied by. Let's take a step back to analyze what's going on here. The partial of the loss with respect to zj is a 404 by 1 vector. In the code, we computed grade z and we saw that grade z was a 404 by 2 matrix where the first column will hold the partial of the loss with respect to z1 and the second column the partial of the loss with respect to z2. Now, zj here is either z1 or z2. So the partial of the loss with respect to zj is a 404 by 1 vector. Let's call that result grade zj as we did in the code. When computing the dot product between grade zj and this element, which is a 404 by 13 modified version of the input matrix, some elements of grade zj will be systematically multiplied by 0 depending on whether or not the corresponding sample was cancelled. Because we are aware of that fact, we can take advantage of it in our code. Let's write a function that will take two arguments as input, the output of the hidden layer zj, and the partial of the loss with respect to it, grade zj. And let's call that function grade ReLU. So grade ReLU will take two arguments zj and grade zj. We know that the partial of zj with respect to its wave vector wj results in a modified version of the input matrix X, where all samples resulting in a negative dot product with wj should be nullified. We also saw that doing so is equivalent to nullifying the entries in grade zj that are multiplied by the cancelled elements. In other words, for each line and each column in zj, if the element is null, replace the corresponding sample in grade zj by 0. Let's go ahead and code it. So for each line in zj, so we go for I in range zj, we take the shape and we grab the first element. So for each line in zj and for each column, so range, we take the second element of the shape. For each line and each column, if the element in zj at that specific location is 0, what we should do is we should replace the corresponding sample in grade zj by 0 and return the new matrix grade zj. I invite you to pause the video and make sure you understand everything we went over. And if you have any questions, just let me know in the comments. I will be more than happy to help.